All right, welcome back. We've got the classic kinetics problem here where we just have a block sitting on a slope. There's some friction between the block and the slope, and we want to determine if the block will stay put due to the friction or if it will slide down, and if so, we want to find out what its acceleration is. So to get started, you'll see that we have up here, we have the static coefficient of friction, 0.7, and the kinetic coefficient of friction, 0.5. So we're going to check first with the static coefficient of friction to see if it's big enough, if it can provide a big enough friction force to hold the block in place. So let's start by labeling on some forces here. We're going to have weight of the block. Weight is equal to mg, which is equal to 50 kilograms times 9.81 meters per second squared. That gives us 490.5 newtons. Now we're also going to want to work in terms of like a different coordinate system than x and y. Let's work in one that we call x prime and y prime. This is because the friction is going to be opposing the impending slip. So impending slip is down the hill, friction is going to be going up the hill. So let's break the weight into its x prime and y prime coordinates. We're going to have y prime like that. So this will be wy prime, and this will be w x prime. So wy prime is just w cos 40 because this angle in here is also 40 degrees. So that's just going to be equal to 490.5 times the cos of 40, which is 375.7 newtons. Wx prime is just w sine 40 because it's including the opposite from that angle, and so that's 490.5 times sine 40, which is going to be 315.3 newtons. There's also going to be a normal force here acting, which is going to be equal and opposite to wy prime. So let's just label on n here, going the opposite direction of the same magnitude, 375.7 newtons in that direction. So then friction, according to the static coefficient, because we're testing to see if the static friction will be big enough. Let's do it over here actually. Let's put the subscript here for static friction. This is going to be equal to mu s times n. Mu s is 0.7 times n, which is 375.7 newtons. So the static friction, the largest static friction force that we can get, is going to be 263 newtons. So when we look at the force balance in the x prime direction, which is the direction of the impending slip, we have wx prime is 315.3 newtons going down the slope, and we have fs 263 newtons going up. So the imbalance is in the downward direction, the negative x prime direction, basically meaning that f prime or fs is not going to be big enough to resist that force caused by the weight. So basically what I'm saying is we have wx prime is bigger than the static friction, and we can see that just it's 315.3 is definitely bigger than 263. So the block will slip because the static friction is not big enough to withstand its weight from sliding it down. So then what we need to do is we need to calculate the actual friction force that's going to be for the kinetic friction, basically because we know the block will be sliding, we have to use mu k. So let's say that we have we'll put the subscript here for fk, kinetic friction. This is going to be equal to mu k n, which is equal to 0.5 times the normal force, which was 375.7 newtons. So the actual friction, the kinetic friction fk, is going to be equal to 187.85 newtons. All right, let's label that on the diagram up here because that's what we actually have, 187.85. And now what we can do is we can apply Newton's second law, which is the sum of forces is equal to ma. We're taking the sum of forces, the positive direction, to be that which is the same as acceleration, which is going to be the negative x direction, because the block is accelerating down the hill. So that's going to be the positive, and that matches what we have for acceleration. So let's take wx prime as positive. So we'll have the sum of forces, we have wx prime, and then we're going to subtract the kinetic friction, and that's going to equal mass times acceleration. We can plug in the numbers, so we have 315.3 newtons minus 187.85 newtons is going to be equal to the mass, which was 50 kilograms, times the unknown acceleration. And we can just do that simplification. The subtraction gives us 127.45 newtons divided by 50 kilograms is going to be equal to A. And if we, again, just do that division, we're going to find that acceleration is 2.549 meters per second squared in the negative x direction, basically down the ramp like that. So let's throw a box around that, and that is our final answer. And just to recap, all we did was we checked for static friction first to see if it was big enough to prevent the block from sliding down. It wasn't, so then we recalculate the friction force that we actually have, which is due to the kinetic friction of the block sliding, and then do the force balance in the direction that the acceleration is going in, taking all the forces with some component in that, taking that component of those forces, summing it up, setting that equal to mass times acceleration, and then quite simply just find the acceleration from there.